Welcome to our deep dive into the fascinating world of numbers. We count, measure, and make sense of the world with numbers, but have you ever stopped to think about what numbers actually are? Where did they come from? And how do they form the basis of mathematics? From counting to complex numbers, we'll uncover their secrets. Get ready to expand your mathematical horizons. Even if you're not a math person, you'll find something amazing. Let's start with the basics. Natural numbers. These are the numbers we first encounter as children. 1, 2, 3, and so on. They're the building blocks of counting, the foundation of mathematics. But don't let their simplicity fool you. Every natural number, except one, can be uniquely expressed as a product of primes, the fundamental theorem of arithmetic. Let's add a special number to our collection, 0. 0 represents nothingness, the absence of quantity. When we combine 0 with natural numbers, we get whole numbers, 0, 1, 2, 3, and so forth. Whole numbers give us a more complete system for representing quantities, including the concept of nothing. The number line extends infinitely in both directions, so we need a way to represent quantities less than 0. Enter integers, which include positive and negative whole numbers, and 0. Integers introduce opposites. For every positive integer, there's a corresponding negative integer the same distance from 0 on the number line. Sometimes we need to represent quantities between integers. This is where rational numbers come in. A rational number can be expressed as a fraction with both numerator and denominator as integers. Rational numbers represent parts of a whole and open up new mathematical possibilities. But here's the mind-blowing part. Not all numbers can be neatly expressed as simple fractions. Some numbers, like the square root of 2 or pi, are known as irrational. Their decimal representations go on forever without repeating in any predictable pattern. Now imagine taking all the rational and irrational numbers and combining them into one giant unified set. This set is known as the real numbers. Real numbers are the bedrock of calculus, statistics, and many other branches of mathematics. What about the square root of -1? No real number, when multiplied by itself, equals -1. Mathematicians invented the imaginary unit denoted by I, where I squared equals -1. Complex numbers combine real numbers with this imaginary unit, forming a plus by, where A and B are real. Complex numbers have applications in electrical engineering, quantum mechanics, and signal processing. Prime numbers are the atoms of the number world. A prime number is a whole number greater than 1 with only 2 divisors. 1 in itself. Prime numbers are fundamental because every whole number greater than 1 can be expressed as a product of primes. They exhibit random patterns and have important implications for cryptography and computer science. Numbers dance to the rhythm of fundamental properties, and the commutative property is one of the most basic. It tells us that the order of addition or multiplication doesn't affect the result. The commutative property simplifies calculations and helps us understand mathematical operations. The Fibonacci sequence is a mesmerizing sequence of numbers where each number is the sum of the 2 preceding ones, 0, 1, 1, 2, 3, 5, 8, 13, and so on. This sequence appears in nature, from the arrangement of petals in a flower to the spirals of a nautilus shell. The Fibonacci sequence illustrates the interconnectedness of math and the natural world. Thank you for joining us on this journey through numbers. From basics to advanced concepts, numbers are the backbone of mathematics and the physical world. Whether exploring the infinite expanse of real numbers or delving into complex numbers, there's always something new to discover in mathematics.